Okay, so we're now ready to do a few example problems. As you can see, the length formula is much simpler. Whoops, I forgot to put the integral sign in. Yeah, it is much simpler that way, but wrong. Now it's from t equals a, or you might call that t initial, up to some b value, t final. That would give us the length of the curve. Okay, but because of the symmetry, the algorithm for solving this is a lot easier. All right, I would say if I were going to break it down into steps, step one, find, possibly simplify dx dt and dy dt. All right, and then you could turn around and after doing that, you just have to take those answers and put the square root of all of them. Pretty much at this point, you can write the integral. So before we had sort of had this 5-step process and there was a lot of algebra involved, I would say that you can probably, once you know dx dt and dy dt, you can write the integral. You just have to remember to square both of them. So let's work with our 2 example problems that we've been doing. Let's start with example 1, where x of t is 2t and y of t is equal to t squared. So now we can real quickly write dx dt is simply 2 and dy dt is 2t. So we're ready. Oh, and this had been on the interval, I believe, from 0 out to 5, I believe we did. So we wanted to find the length of that line. So now we have those things. We can pretty much write the length integral. This is the integral from t equals 0 out to 5 of the square root of, and now just be careful. Let me actually emphasize by writing 2 squared plus 2t squared dt. All right, so let's simplify that down. That's the integral from 0 to 5 of the square root of 4 plus 4t squared dt. You may notice that there's a factor of 4 on both terms, and if we draw that out of the square root, it becomes a 2. So this could simplify down to twice the integral from 0 to 5 of the square root of 1 plus t squared dt, right? Now, it turned out we're stuck. We don't have anything in our bag of tricks to evaluate that. So that is the integral that would give us the length, but at this point, since we don't know how to find the antiderivative of that function, we cannot use the fundamental theorem of calculus. It's out. We need to know the antiderivative to take to be able to the fundamental theorem of calculus. So we remind you, is the integral from a to b of f of x dx is the antiderivative at b minus the antiderivative evaluated at a. We can't use that since we don't know the antiderivative, so we'll use numerical methods, which basically means grab your calculator or grab MATLAB or use the code that we just wrote and with a large number of subintervals and see what the value is approaching. All right, so that's how we would do it. But you can see how easy it was to set this problem up. Right, let's do our other example and show how easy it is to set it up when we're in parametric equation form. So for example 2, we've been working with x is equal to 2 cosine of t and y is equal to 3 sine of t. So dx dt is simply negative 2 sine of t. When we square it, the negative won't matter. Dy dt is simply 3 times the cosine of t. So the length, look at how fast this is the integral. Oh, and we went from, this was on 0 to 2 pi for t. We wanted to go all of the way around our ellipse. So t went from 0 to 2 pi. And we could then put in the square root of, if we square dx dt, I'll write it in 2 steps. You don't really need to write that negative sign. Make sure you put it in parentheses if you do. Okay, so here we go. The length, t equals 0 to 2 pi, the square root of 4 sine squared t plus 9 cosine squared of t dt. And once again, we are stuck. So we're going to have to switch to numerical methods. We cannot use the fundamental theorem of calculus because there is not an antiderivative that we know. Now, if this had been a circle, it would be easy to do. Let's just change them both to, let me write it this way. Let's let x equal just cosine of t and y equal to the sine of t. Instead of having the 2 and the 3 in front, if we had done that, we would have come up with the integral from 0 to 2 pi. And we would have simply had sine squared t plus cosine squared of t. And hopefully you're having an aha moment here. It would be beautiful if it's a circle. We would integrate from 0 to 2 pi. And sine squared plus cosine squared is 1. And the square root of 1 is 1. So it would be this easy. It would be the integral from 0 to 2 pi of dt. The antiderivative would simply be t, evaluated at 0 and 2 pi. And the answer would be 2 pi. Because what is the circumference of a circle of radius 1? It is just 2 pi. If there had been any other r value in here, if we put an r value here, this would become r squared with an r squared. We would draw it out. We would get an extra factor of r and an extra factor of r, an extra factor of r, and that would become 2 pi r. So it would work beautifully for a circle. We wouldn't need any our identity properties would be, all we'd have to be able to use is the sine squared plus cosine squared equals 1. So that would be a simple identity to pull out in order to finish that problem. I want to just pause and show you one more thing about where this all will be going next year. So let me switch over to MATLAB real quickly. Okay, so here we have a code, a line integral code in MATLAB, and this is based on parametric equations. So you can actually see the parametric equations right here in the code. X and Y are given by cosine t and 2 sine t. But we have another function, a z function, a height function, that's x times y. And let's see what happens when we run this code. Oh, look at that. We have a figure forming in 3-dimensional shape. Oh, that's really neat. Let's run that again. So we have a figure that's being shaped out, all right? And the blue plane is the XY plane. In fact, let me undock the figure here so you can see it. It'll be bigger. Let me go full screen. Whoops, let me maximize that. Okay, so our figure is full screen, and you can see I can rotate it around here. So what happened is we went around an ellipse, but in the 3rd dimension, the z direction, we had height depending on where we were as we made our way around the ellipse. And within those little regions of height, okay, you can see we've carved out what look like little trapezoidal sums, right? All that we've done is we're doing a Riemann sum here, but it curves around and follows the curve of the ellipse instead of just going along the x-axis. So you can actually integrate along a curve. So we're just integrating our way around an ellipse to get the height values. And the widths of these Riemann sums are given by the little length segments. Okay, remember we found the length elements. So the widths of these are given by those length elements on our way around the curve. And then we simply multiply by the z value to get the area of each one of those panels. All right, so we have some positive contributions at the beginning of this, and then we have some negative contributions and then some more positive contributions. If I go back and look at the code, and let's, instead of having x times y, let's square both of those things, x dot. So then we'll only have positive contributions. Okay, whoops, MATLAB's having a little bit of trouble catching up here. So let me see, yep, it's not catching up. So we'll just stop there, but you can get a little taste of the things that are to come.